Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 8.5 titled More Inductive Proofs. So hopefully you've seen my video on Section 8.4, because in that section we were introduced to proving statements involving integers by the principle of mathematical induction, where you show that a certain base case is true, and then you prove that for all integers greater than or equal to that base case, all integers k, if the statement is true for k, then the statement is true for k plus 1. It's called the inductive step. So again, hopefully you've seen section 8.4, because I'm just going to go right into these proofs. It's the same steps as in section 8.4. Yeah, like I said, I'm just going to get right into it. Alright, so here we have a divisibility proof by induction. So I'm just going to do this on paper and show you, hopefully refresh your memory as to what a proof by induction looks like. So here's the statement of the theorem. It's for every positive integer n. Right, so that would mean for every n, greater than or equal to 1. Right, the positive integers start at 1 and then go 2, 3, 4, and so on. For every positive integer n, 3 evenly divides 2 to the 2n power minus 1. Right, so this is a statement here about positive integers, integers 1 and up. And typically when you have a statement involving integers from a certain integer up, we can try a proof by mathematical induction on the value of n. So a proof, and this is going to be a proof by induction on n, right, the value of n here. Right, and as I did in my last video, before I go into proving anything, let's see if we even believe this statement that 3 will evenly divide 2 to the 2n power minus 1 for values of n greater than or equal to 1. So again, this is separate. This is not the proof. These are just some examples. So I'll start with n equals 1. Does 3 evenly divide? Is this a true statement? 3 evenly divides 2 to the 2 times 1 power minus 1. Well, that's 2 squared minus 1. That's 4 minus 1. That's 3. Yes, right? 3 does go into 3 evenly. How about when n equals 2? Does 3 evenly divide 2 to the 2 times 2 power minus 1? Well, this would be 2 to the 4th minus 1. That's 16 minus 1. That's 15. That's 3 times 5. Yes, 3 goes into that evenly. So again, this is not a proof. You could do it for n equals 3, n equals 4, and see if the statement is true. But it doesn't show, it doesn't prove that for every positive integer the statement is true. But we're just getting an idea here. I'm just trying to say, hey, do I even believe that this statement is true? And after even these first couple examples, I do believe it. All right. So let's prove it by induction. Now the lowest integer that we're starting at here is 1, so that's going to be our base case, and I kind of already showed that, but I'll rewrite it. The base case, when n equals 1, we have the statement, 3 evenly divides 2 to the 2 times 1 minus 1. Now let's see if that's true. Right? That's 3 evenly divides 4 minus 1, 3. And this is true. Right? Now, I'm going to stop writing the evenly divides thing. Remember, if I want to say 3 evenly divides, two to the 2n minus 1, that's the same thing as saying 2 to the 2n minus 1 is a integer multiple of 3 is equal to 3 times, some k. I'll say 3 times m. 3 times m for some integer m. Right, m belonging to the integers. So this is a side note. This isn't even actually part of the proof. Right, this is a little side note here, just saying an equivalent. What's an equivalent statement to saying that 3 evenly divides something? Right. Okay, so I've got the base case. Right, when this statement is true when n equals 1. All right, now let's show that if it's true when n is 1, then it's true then it'll be true when n is 2. And if it is true when n is 2, then it'll be true when n is 3. And if it's true when n is 3, then it'll be true when n is 4, and so on and so forth. This is the inductive step. And the inductive step is the heart of the proof, right? It's where you're actually proving a statement. You're trying to show that for all integers k greater than or equal to that base case integer, right? For all integers k greater than or equal to 1, if the statement is true, right? If this statement is true when n equals k, so if 3 evenly divides 2 to the 2k minus 1, we're going to show that if that is true, then the statement will be true when n equals k plus 1, right, for the next integer up. Then 3 will evenly divide 2 to the 2 times the quantity k plus 1, then minus 1. All right. So what we're going to assume here, right, remember when you're trying to prove an if p then q statement, you assume p, and then through some series of logic, you show that q is true. So we're going to assume here, that 3 evenly divides, right, this thing here, we're assuming this statement is true, the hypothesis. We're going to assume that 3 evenly divides 2 to the 2k minus 1. And this is called the induction hypothesis. Right, what we're assuming to be true in the inductive step. Right. Now, as I mentioned earlier, this means, by the definition of divides, right, this means that 2 to the 2k minus 1 is equal to 3 times m for some integer m. All right. So again, this is just another way of wording the induction hypothesis. We are assuming that this statement is true. And now what I want to show is that if this is true, then 3 also evenly divides 2 to the 2 times k plus 1 minus 1, right, when n is k plus 1. So again, you can't assume that. We have to show it, assuming this is true. And we're going to use this at some point. Right? We're going to use this fact, this assumption, this induction hypothesis at some point. Well, now let's look at the expression that we're trying to figure out here. I'm trying to show that 2 to the 2 times k plus 1 power minus 1 is some multiple of 3. So let's look at that expression. 2 to the 2 times k plus 1 power minus 1. And notice this does not involve anything we're used to yet. I want to eventually use again the induction hypothesis. Now the induction hypothesis involves 2 to the 2k power, not 2 to the 2k times k plus 1. So I'm going to do a little algebra here. I'm going to eventually get this so that there's 2 to the 2k involved. So distributing the 2 there, we have 2 to the 2k plus 2, all right, 2k plus 2, and then minus 1. And then using some properties of exponents, this is 2 to the 2k times 2 squared. So this is 4 times 2 to the 2k. Right? That's 2 squared times 2 to the 2k. That's that. And then minus 1. All right. Now here's where I can use the induction hypothesis. We have assumed this to be true, that 2 to the 2k minus 1 is equal to some multiple of 3, 3 times m, right, where m is an integer. Now if I play with this a little bit, that would mean that we're assuming that 2 to the 2k is 3 times some integer m plus 1. And this is where we're going to use our induction hypothesis. So I started off with this 2 to the 2k plus 2 times k plus 1 power minus 1. We got it now to involve 2 to the 2k, and then I can use the induction hypothesis to say, hey, 2 to the 2k, that's some multiple of 3 plus 1. So by our induction hypothesis, this is equal to 4 times, and then again 2 to the 2k is 3m, 3 times some integer m plus 1. And then we got minus 1 after. And after some distributing here, this is 12m plus 4 minus 1, that'd be plus 3. And oh look, don't these both have a common factor of 3? This is 3 times 4m plus 1. And because m is an integer, 4m plus 1 is also an integer. So we have just shown, right, therefore 3 does evenly divide. 3 does evenly divide this 2 to the 2 times k plus 1 power minus 1. So we have shown that if the statement's true for k, then it'll be true for n equals k plus 1, the next integer up. And because of our base case, we've shown it was true for 1. Well, if it's true for 1, then this says that it's true for 2. And if it's true for 2, then this inductive step says that it's true for 3, and then it's true for 4, true for 5, true for 6, true for 7, for all positive integers. Therefore, we have now just shown that 3 evenly divides 2 to the 2n minus 1 for all positive integers n. And I'm done. There's the proof. Proof by induction. Okay, so again, base case, inductive step. if it's true for k, then it's true for k plus 1. You assume it's true for k, show it's true for k plus 1. And your base case, if it's true, will start a domino effect that will show you it's true for all integers after the base case. All right. So again, you can read through their proof here. I think looks about the same as mine. Now, I'm going to leave these to you. Here's another one where you have to prove that for every positive integer n, 4 evenly divides this expression. It's pretty much the same kind of proof. So I'll leave that to you. All right. Here's an induction proof involving a recurrence relation. So let me show you how this will work out. So here I'll write this on some paper and we'll do a proof by induction on the value of n. Right. So it says here, define the sequence Gn, G sub n, in the following recursive way. Right? Remember, this is a recurrence relation where you define how the value of each term depends on previous terms. See, every term here is 3 times the previous term plus 2 times the value of the index. But every term depends on the value of the previous term. And then they're saying that if this is the way the recurrence relation is defined, then for any n greater than or equal to 0, so now my base case is going to be at 0, G sub n will be 5 halves times 3 to the nth power minus n minus 3 halves. So here they're giving us an explicit formula for this sequence defined recursively up here. All right, so let's see, I'm going to go with some paper and we'll prove this by induction. So again, we're given this definition of a sequence, and again, we're asked to prove that for any n, any integer n greater than or equal to 0 this time, the nth term of this sequence, or the n plus first term of this sequence, right, because we're starting at g0, so gn would be the n plus first term, is 5 halves times 3 to the nth minus n minus 3 halves. So again, before I even prove it, before I prove this, I'm going to see if I believe it first. All right, let's go over several examples. So again, this is not the proof. This is just me doing some scratch work to see if I even believe this. All right. Now, we know that G0 is 1, right? So the first term of this sequence is 1. And I'll start writing the terms up here. Then G1, following this rule, whenever n is greater than or equal to 1, G1 would be 3 times G0 plus 2 times 1, right, because n is 1 here. So this is 3 times 1, right, G0 is 1, plus 2 times 1, that's 5. All right, so the second term is 5, that's when n equals 1, right? This is when n equals 0. When n equals 2, you got G2 equals 3 times G1 plus 2 times 2, just replacing n with 2. So this is 3 times 5 plus 4. This is 15 plus 4, that's 19. All right. And I'll do one more. And then let's compare this to the formula they gave. Right? We're trying to show that the rule for this sequence is given by this explicit formula. And then for n equals 3, G3 would be 3 times G2 plus 2 times 3. That's 3 times 19, right? G2 is 19. Plus 6. And 3 times 19 is 57. Plus 6 is 63. All right, and so on. All right. So let's see if this actually works for our explicit formula. Let's see. So using the little formula there that they gave us, let's see if that formula is actually working out. Now again, just because I'm showing it works for these four doesn't prove anything. Just means it works for these four. Showing a few examples doesn't show that it works for all n greater than or equal to 0. This is just me trying to feel it out, trying to see if I believe the statement. Now, when n equals 0, we have g0 equals 5 halves times 3 to the 0. That would just be 5 halves times 1, minus 0, minus 3 halves. 5 halves minus 3 halves is 2 halves. That's 1, and that matches. That matches the g0 there. When n equals 1, if I use this formula, it'd be 5 halves times 3 to the first, so that's 15 5 halves times 3, 15 halves. Minus 1, minus 3 halves. Now 15 halves minus 3 halves, that's 12 halves, which is 6, minus 1 is 5. That also that matches the next term. And I'll do one more. When n equals 2, g2 equals 5 halves times 3 squared. 5 halves times 9. So it'll be 45 halves minus 2 minus 3 halves. And 45 halves minus 3 halves is 42 halves, which is 21 minus 2 is 19. That also matches. So even just from these first three terms, I feel like, the formula they gave is true. This isn't a proof, but I feel like it's good. So now I'm going to prove it. And we're going to prove it by induction on the value of n, starting with n equals 0, right? This has to be true for, when n is 0 or greater. So again, the proof here is going to be by induction on the value of n. And our base case this time is when n equals 0. Now, when n equals 0, if I look at the formula here, it says, I already wrote this up, so we already see that it's true. g0 equals, 5 halves times 3 to the 0 minus 3 halves. That's equal to 1. And, we were given g of 0 is 1, so the statement is true when n equals 0. The term of the sequence when n is 0 is 1 here. The term of the sequence described by this rule is also 1 when n is 0. So the statement is true for this base case. Well, I'll just say a statement is true, right, for when n equals 0. Next comes our inductive step. So we're going to show that for all k, for all integers k greater than or equal to that base case value, for all integers k greater than or equal to 0, if this statement is true for k, right? So if the k, if when n equals k, the value of the sequence, the term is actually going to be 5 halves times 3 to the k minus k minus 3 halves. We're going to show that if that is true, then it'll be true, the statement will be true when n is k plus 1 as well. G of, g sub k plus 1 will be equal to 5 halves times 3 to the k plus 1 minus the quantity k plus 1, right? Just replacing all the n's with k plus 1 this time, minus 3 halves. Which I guess if I want to simplify that a bit, that would be 5 halves times 3 to the k plus 1 power, then minus k minus 5 halves, right? Because it'd be minus k minus 1, but that's minus 2 halves, minus 3 halves would be minus 5 halves. So either one. All right. So remember, to prove that, and if then statement, we're going to assume that this is true for integers greater than or equal to 0, for some integer k, integers k greater than or equal to 0, and then show that the statement is true when n equals k plus 1 for the next integer up. And since we've shown it was true for 0, then this will imply that it'll be true for 1, and then if it's true for 1, then it's true for 2, if it's true for 2, then it's true for 3, and so on and so forth. And the statement will be true, proven true, for n greater than or equal to 0. Alright, so our inductive hypothesis, what we're going to assume. We're going to assume that for integer k greater than 0, so for integers k, for integer k greater than or equal to 0, g sub k is equal to 5 halves times 3 to the k minus k minus 3 halves. Sorry, so minus. We're assuming this. This is our induction hypothesis. Oh, sorry. Induction hypothesis. So I eventually want to use this. And we're going to try to show that g sub k plus 1 will be equal to 5 halves times 3 to the k plus 1 minus the quantity k plus 1 minus 3 halves, or this down here. Now again, if you're trying to show this, you can't use it. You can't start with it. You either got to start with one side or start with the other side and work your way to the other side. So I'm going to start with the left here. So let's look at the term g sub k plus 1. So look at g sub k plus 1. Now, since k is greater than or equal to 0, k plus 1 is going to be greater than or equal to 1, right? Just adding 1 to both sides. So that means that this subscript, right, this k plus 1, the subscript, the index on g here, is greater than or equal to 1. And remember, for this sequence, the way it was defined, way back here, if the subscript was greater than or equal to 1, we could apply this rule. The way that term was found was by applying this rule. So, g sub k plus 1, since k plus 1 is going to be greater than or equal to 1, will be equivalent to 3 times g sub k plus 2 times the quantity k plus 1. Right? Because remember, it's 3 times g with a subscript that's 1 less, right? Plus 2 times that subscript. Right? Plus 2 times that subscript. Right? Okay. Now, our inductive hypothesis involved g sub k. And look, I'm seeing g sub k right here. So I can apply what we have assumed to be true. I can apply this inductive hypothesis right here. So by the inductive hypothesis, or by the induction hypothesis, this is equivalent to 3 times, and we have assumed that g sub k is equal to 5 halves times 3 to the k minus k minus 3 halves. Alright, and that's just replacing g sub k, and then we've got this, plus 2 times the quantity k plus 1. Alright, and that was again by the induction hypothesis. Sorry about the clutter over there. And now I'm hoping that this expression here I'll eventually have be equivalent to one of these things, right? I want to show that g sub k plus 1 is equal to one of these things. Alright, well, in distributing the 3 to all these terms here, I have 5 halves. This is equivalent to 5 halves times 3 to the k plus 1, right? Because it's 3 times 3 to the k there. then minus 3k minus 9 halves. And then here I'm going to distribute the 2, right? This 2 times k plus 1 here. We got plus 2k plus 2. And combining some like terms here, this is 5 halves times 3 to the k plus 1. Then negative 3k plus 2k, that's minus k. Negative 9 halves plus 4 halves is negative 5 halves. And this is exactly what I had here that I said I was trying to show. So we have shown that if the statement was true for k, then it will be true for k plus 1, the next integer up. And since we've shown the base case, we showed it was true for n equals 0. This whole thing implies that it's then true for 1, and if it's true for 1, then it's true for 2, and if it's true for 2, it's true for 3, and so on. So after all this, therefore we have shown inductively that g sub n is equal to 5 halves times 3 to the n minus n minus 3 halves for all n, all integers n greater than or equal to 0. Done with the proof. All right. So again, you got that base case and inductive step. If it's true for k, greater than or equal to the base value, then it's true for k plus 1. You can show those things. You can make a proof by induction. All right. So there's a couple examples. I'm going to go through the whole thing there. Here's another one. Again, this will be very, very, very similar. So you can read through that if you want to do these activities. And they do another one. I'll do one of these. They have inductive proofs showing, remember those closed forms for the sums of an arithmetic or geometric sequence? Right, when you add up the first n terms of an arithmetic sequence or the first n terms of a geometric sequence, there were some formulas to help you find those sums. That was from section, I think, 8.3. Well, here we're actually proving that those formulas are correct, proving by induction. So I'll do the one for the arithmetic sequences, and then you can take a look at the one involving geometric sequences. And they've got animations for you and all that. They take you through them. So, I'll do it on paper though. Right. So here we're asked to prove that, for any integer n greater than or equal to 1, so our base case is going to be when n equals 1, the sum from j equals 0 to n minus 1 of a plus jd, where again a was that first term of the sum of the sequence that we're adding, d was that common difference, right, that number you kept adding to get from one term to the next in an arithmetic sequence. This sum will be equal to a times n plus, the value of d, the common difference, times n minus 1 times n in the numerator divided by 2. Alright, so I'll just jump right into it. I'm not going to do any, hey, do I believe it examples. So let's do a proof. And we're going for all values of n greater than or equal to 1. So I'm going to do a proof here by induction on n. Right. Induction on the value of n. Sorry, by induction on n. Alright, so the base case. When n equals 1. The lowest value here. Well, we have the sum from j equals 0 to 1 minus 1, so 0. Right? I'm just replacing n with 1 of a plus jd. Is that equal to a times 1 plus d times 0 times 1 divided by 2. So basically, is it just equal to a? Well, what would be over here? From j equals 0 to 0, I just replace j with 0. This would be a plus 0d. That's just a on the left side. You have a times 1, that's a on the right side, plus 0. This is true. Right, so that particular sum is true when we're in the base case, right? We're on the lowest integer there when n equals 1. All right, next comes our inductive step. So we're going to try to show that for any integer k greater than or equal to 1, for any integer k greater than or equal to 1, greater than or equal to our base value, if this statement is true for n equals k, so if the sum from j equals 0 to k minus 1 of a plus jd, if that's equal to a times k plus d times k minus 1 times k divided by 2, if this is true, then we can show that, then we'll try to show the statement is then true when n equals k plus 1. Then the sum from j equals 0 to, again, I'm just going through and replacing all the n's in this statement now with k plus 1. Now if I replace n with k plus 1, k plus 1 minus 1 is just k, so now this is k. The sum from j equals 0 to k of a plus jd is equal to a times k plus 1 plus d times k, right, k plus 1 minus 1, then times k plus 1. Replacing all the n's with k plus 1, and then that divided by 2. Right. So again, I'm not going to write out the sentence again. This if part, the part with the if, we are going to assume that this is true. Right, I am going to assume this. This is again called the induction hypothesis. Right. And we're going to use it somehow to then show this last statement, that the statement I had here is true when n equals k plus 1. I'm assuming it's true for when n equals k, and showing that it's going to then be true when n equals the next integer up, k plus 1. All right. So, again, we can't start with this equation. We have to show it. So I'll just start with one side and work our way to show that it's actually equal to the other side, and we'll have verified it. So I'll start with the left here. The sum j equals 0 to k of a plus jd. Right. And we're going to eventually show that it is indeed equal to this right side I've got. Now, we eventually want to use the induction hypothesis. I want to use this statement that I circled here. Now this statement involves the sum from j equals 0 to k minus 1, not to k. So what I can do, from 0 to k is just from 0 to k minus 1, and then plus the final term with k. So I can rewrite this so that we pull out the final term. So this is equal to the sum from j equals 0 to k minus 1 of a plus jd, and then plus the final term when j is equal to k. Replace j with k. So a plus kd. Okay, so these are the same sums. They'd have the same exact terms. But now, look at this. I have this sum from j equals 0 to k minus 1 of a plus jd. That's this. And by our induction hypothesis, what we have assumed to be true is that this is equal to ak plus d times k minus 1 times k over 2. So I'll use that. So by our induction hypothesis, this is equal to, I already forgot what I said, a times k, this sum in orange here, plus d times k minus 1 times k over 2. And then don't forget I have this last term that I pulled out still, plus, and then a plus kd. All right. Now, what I'm eventually trying to do is show that this expression now, I want to get it to be this guy up here. Right? This right side. I start with the left side. I want to eventually show that's equal to this right side. And then we'll have shown that the statement is true for k plus 1 when it's true for k. All right. Well, notice I have a, k, a here. So those make a times k plus 1 when I factor a out. Right? Those two terms, I factor a out, I'll have k plus 1 less. So there's that. Then this is kd over 1. I'm going to try to put this with this fraction, so I need to multiply this here by 2 over 2, get a common denominator of 2. So then I have plus, and then putting this and this together, I have a common denominator of 2. And then I have d times k minus 1 times k plus, and then up here 2kd or 2dk. And then something I'm noticing is that both of these terms in my numerator have a d and a k. All right, they both have dk, so I can factor that out. So this is a times k plus 1 plus, and then both of these I pull dk out. And if I pull dk out, what's left over is k minus 1 plus 2. Well, that's just k plus 1. And then we have over 2, and this is exactly what I had up there. Exactly. So I have shown that the statement is true when n equals k plus 1 if it's true for n equals k. Therefore, our statement is true, because we showed it also true for the base case of 1, and therefore it would be true for 2, and then true for 3, and then true for 4, and so on. Therefore, the sum from j equals 0 to n minus 1 of a plus jd is equal to a times n plus d times n minus 1 plus times n over 2 for all n greater than or equal to 1. All integers greater than or equal to 1. We have just shown that by induction. Base case, inductive step. Same process every single time. And when you're trying to show that that k plus 1 case is true, you're going to have to use the fact that it's true in the kth case. Right, that's your induction hypothesis. You assume it's true for n equals k. You show it's true for n equals k plus 1. And then you can look at they do the same kind of thing for that rule for the geometric series. So I'll leave that to you to read and follow through. And this is just going through the steps. So I already kind of went through some of these steps. You can look at that. All right, then they have one last one here. And again, I'll just leave this to you to read. It's the same kind of proof. An inductive proof for set operations. So here they're trying to prove, they're trying to prove the generalized De Morgan's law. So prove that if I do A1 intersect A2 intersect all the way up to intersection of n sets, AN, and take their complement, that'll be equivalent to the complement of A1 union, complement of A2 union, complement of A3 union, all the way down to AN. We can do this with induction on n, right? Because this is good. We're going from n equals 2 or greater. So I see the base case is at 2. If you do the induction, if you do the A1 intersect A2 complement, that's A1 complement union A2 complement. That's something you already knew. That was De Morgan's law, right? De Morgan's law applied to two sets. So it's true for the base case of 2, and then you assume it's true up to k, and it's true for the intersection of k sets, and try to prove that it's true for the intersection of k plus 1 sets. And then you see they take this k plus 1 set intersection, break it up, and you have the first set from A1 to AK, they call that set B, and then intersected with AK plus 1. The intersection of two sets, you can apply De Morgan's law. And then this intersection of B is the intersection of the K sets, and then you can apply your induction hypothesis and say, oh, look, it's great, it works for K plus 1 as well. I mean, like, I'm not writing that out. You can watch the animation. It's the same steps. It's the same steps. Base case, induction step. You assume it's true for K, all K greater than or equal to your base value, and then show that it must then be true for K plus 1. They say, what's the induction hypothesis? Come on, easy enough. Then you have your additional exercises, right? Some of these will be in your assignment 8 homework. Some will not. I would still recommend looking at all of them, trying to work on all of them, do all of them, get more exposure to the material, more practice, get better at it. This is an important proof technique. And you can also view solutions, see how they're doing things. Again, I would recommend trying to do things on your own first before you resort to looking at the solutions. Because if you're just looking at the solutions and copying them down, you're not really learning anything. Okay, so try to work on them on your own. And of course, if you have any questions, send them my way, let me know. And thank you very much for watching.